Good morning, students. Yesterday, we discussed the definition of ring and abelian ring and also one theorem. We have learned one theorem. Now, we are going to the second theorem. What is the definition? What is learned in the previous class is definition of ring. What is the definition of ring? A non-empty set R with respect to two binary operations, addition and multiplication, that is plus and dot, is called ring if it satisfies the following laws. But the first condition is the R plus is abelian group, and the second one is R dot is semi group. The third one is distributive laws holds. If these three conditions were satisfying the non-empty set R, then that set R with respect to plus and dot, that is R plus dot, is said to be ring. What are the examples for this one? A set of integers Z plus dot and set of real numbers R plus dot are both are the examples of this ring. And the definition of abelian ring, a ring R plus dot is said to be abelian ring if it satisfies the abelian law with respect to multiplication, that is A dot B is equal to B dot A. The examples are the same for the ring also, that is set of integers Z plus dot and set of real numbers R plus dot. Both are the examples of this abelian ring. After that, now we learn the definition of Boolean ring. What is Boolean ring? A ring, here is also a ring, R plus dot, is called Boolean ring if A square is equal to A for all A comma B belongs, for all A belongs to R. That means in that ring R, if we take an element A, that square, A square is equal to itself, A. If we take B belongs to R, then B square is equal to B. If we take C belongs to R, then C square is equal to C. These type of elements are called, this type of A, B, C. If A square is equal to A, B square is equal to B, C square is equal to C. Such type of A comma B comma C elements are called idempotent elements. Okay, right. If in that ring all the elements are like that, satisfying this type of condition, then that ring is said to be Boolean ring. That is the definition of Boolean ring. What is a Boolean ring? A ring R plus dot is called Boolean ring if A square is equal to A for all A belongs to R. Right. Now we do the theorem 2. We prove the theorem 2, that is on the Boolean ring. What is the statement? If R is a Boolean ring, then R is abelian for all A comma B belongs to R. That means if we take R is a Boolean ring, then that R is abelian for all A comma B belongs to R. Or there is another statement is there. If R is a Boolean ring, then A plus A is equal to 0. The second bit is A plus B equal to 0, then A is equal to B. The third bit is that B is equal to B dot A for all A comma B belongs to R. You observe that in the first statement, Boolean ring, then abelian. We have to take Boolean ring, then we have to prove abelian. In the second statement, if R is a Boolean ring and we have to take Boolean ring, then we have to prove 3 bits. In the third bit, there is an abelian law. But before that, we have to prove 2 bits, that is A plus A is equal to 0. In the second bit, if A plus B equal to 0, then A is equal to B. The last bit is, the third bit is A dot B is equal to B dot A, which is the abelian condition for all A comma B belongs to R. So, if you see the statement in the examination paper, that is a university examination paper like that, then you have to prove these 2 bits also before the abelian condition. With these 2 bits only, using these 2 bits only, you can prove this abelian law. So, students, you have to remember these 2 bits for this theorem if you got the question like this first statement, that is R is a Boolean ring, then R is abelian in the question paper, examination question paper. So students, now we are going to the proof. This proof is also in 2 pages. This is the first page of the 2 pages. Now, what is that? We have to take R is a Boolean ring. That is, suppose R plus dot is Boolean ring. I am taking the elements 0, A, B in R. A is an element in R. What is R? R is a Boolean ring. Boolean ring means A square is equal to A. B is also in R. R is a Boolean ring. That means B square is equal to B. 0 is also in R. That means 0 square is equal to 0. It's already well known. That's why 0 square is equal to 0 is not written here. Okay, right. A is in R. A square is equal to A. B is equal to in R. B is in R. B square is equal to B. Okay, right. Now I am proving the first bit, that is A plus A is equal to 0. What is the first bit? For that one I am taking for A comma A belongs to R. I am taking a single element A in 2 times, that is A comma A belongs to R. R is what is the R? R is a ring. Ring means it is an abelian group with respect to addition. That means by what is abelian group? For 5 laws must be satisfied in the abelian group. What are they? Closure law, associative law, identity law, inverse law, and abelian law. In these 5 laws, I am using the first law, that is closure law. By closure law, A plus A is also belongs to R. What is R? R is a Boolean ring. Boolean ring means any element in R, its square is equal to itself. That means A plus A is an R. That's why A plus A whole square is equal to A plus A. If you see here, A is in R, then A square is equal to A. B is in R, B square is equal to B. Similarly, A plus A in R, A plus A whole square is equal to A plus A, because R is a Boolean ring. A plus A whole square can be written as A plus A into A plus A. And RHS part A plus A is as this. Now I am writing that this A into A plus A plus A into A plus A. Are you observe that? A into A plus A plus A into A plus A. I am mentioning here one A is in red color with underline and the second one is in blue color. So you can easily understand that which A was distributed both sides. Okay, right, and RHS part is A plus A as it is. And the LHS part, A into A plus A. This A is distributing these 2 elements by the distributive laws. That is A into A plus A into A. That was written in the next step. And plus A dot A plus A. This is also distributed the same. That is A dot A, very good, plus A dot A. And the RHS part is as it is A plus A. A dot A means A square plus A dot A means A square plus as it is A dot A means A square plus A dot A means A square plus is equal to A plus A can be written as A plus A plus 0, because 0 is the additive identity. That means A plus A can be written as A plus 0. Okay, right. What about A square? We have learned that A is in R. R is Boolean ring. That's why A square is equal to A. So we can write A square as A. Here also A square is A plus A square is A plus as it is A square A plus A square A. A square can be written as A is equal to A plus 0 or RHS condition is same. If we observe on the both sides, A plus A is on left side. Here is also on the RHS part, A plus A is on the left side of the RHS part. Are you observe that in both sides? So I am cancelling by left cancellation of these 2 A plus A's. A plus A, A plus A, A plus A. If this cancelled, this A plus A was cancelled, the remaining A plus A was going to the next step. Here is also in this one, A plus A was cancelled, then 0 will be going to the next step. That means A plus A is equal to 0. Okay, what is that first bit? A plus A is equal to 0. It was proven. Are you observed that? Right. Next we go to the second bit, that is, what is the second bit? A plus B is equal to 0 we have to take in, then we have to prove A is equal to B. We have to take A plus B equal to 0 and then we want to prove A is equal to B. For that I am taking that A plus B equal to 0. If you see that in the proof of page 2 of 2, the second bit, let, what you have to take? Are you students, are you following the cursor or not? You must All of you must follow the cursor. A plus b equal to 0 we have to take. That's why I taken that, let a plus b equal to 0. Okay, right? A plus b was going to the next to the same. G is equal to, instead of 0, what is 0 from the first bit? First bit was given. What is 0? 0 is equal to a plus a. We can write a plus a in the place of 0. Is it right? So I am returning it 0. I am replacing 0 with a plus a by 1. Okay, right? If you observe that on the LHS part, left side is a. On the RHS part is on left side a. By cancellation, by left cancellation, I am cancelling these two a's. Then what remains in the LHS? A cancelled, so B goes to the next step. Here this A was cancelled, so the another A goes to the next step. Then what happens? B is equal to A. We have taken A plus B equal to 0. Then we show that A is equal to B. Is it right? What is the second bit? Go to the red lines. Red question, that is question. What is the second bit? A plus B equal to 0, then A is equal to B. It was proved. A plus B equal to 0, then A is equal to B. Second bit is also completed. What about the third bit? For the third bit, you have to take A comma B, two elements. So, if we are going to the third bit proof, for A comma B belongs to R. I am taking the two elements, A comma B belongs to R. R is ring. Ring means it satisfies R plus abelian group condition is there. R plus abelian group means with respect to plus, closure, associative, identity, inverse, and abelian laws must satisfies. That's why I am using closure law with respect to addition for the elements A comma B. That means A plus B belongs to R. This is a closure law condition. Okay, right. What is R? R is a Boolean ring. What happens for the Boolean ring? If you observe that if R is a Boolean ring, A is in R, A square is equal to A. B is in R, B square is equal to B. A plus A is in R, A plus A whole square is equal to A plus A. Here is also A plus B in R. That means A plus B whole square is equal to A plus B. Because R is a Boolean ring. That's why A plus B whole square is equal to A plus B. This A plus B whole square can be written as A plus B into A plus B. That is equal to A plus B. This A was distributed to this thing, A into A plus B plus B into A plus B, A into A plus B plus B into A plus B is equal to A plus B as it is. RHS part is same. Then what happened to the next part is A into A plus B can be written as A into A plus A into B plus B into A plus B into B. That is equal to A plus B. Okay, students. Here is a small mistake. If you observe that, all of you not observing clearly. If you observe that the bit is a small difference is there. Here, this is right distributive law. Are you understand that? Because what is there? What is that one? Kindly understand that. What is that? A plus B on right side, it was distributed to this A and A plus B. Okay? Okay, right. For this one also, we have to correct it. This was perfectly written. The previous one also right distributive, left distributive, right distributive. Okay, right. This was corrected. Are you following that? This is right distributive. Are you understanding that or not? Why it was written like that? A small mistake was done in the proof. In typing mistake is there. If you observe that, here this A plus A is distributed for the A on right side. The total element A plus A distributed to these two is distributed to these two terms, A into A plus A into A plus A. Similarly, if we go here also, A plus B is total A plus B is distributed to these two terms, A into A plus B, B into A plus B. A plus B is distributed, that is on the right side. So this is called by right distributive law. But when we go to this step, A into A plus A into B. A distributed to these two terms. A is on left side, that is by left can distributive law, we have written like that. Here is also B into A plus B is B dot A plus B dot B. A plus B is as it is. What is A into A? A square plus AB as it is plus B dot A as it is plus B dot B is B square. And I am writing here A as A plus 0. A as A plus 0 because 0 is the identity. A plus 0 is A. That's why I am replacing A with A plus 0. Plus B is as it is. Okay, right. What is A square? Because A is in R. A is in R. Then A square is equal to A. If B is in R, B square is equal to B because R is Boolean ring. Here is also A square is equal to A. I am using the same one. A square is equal to A. I am replacing A square with A. Plus AB is as it is. Plus BA as it is. Plus B square. B square means B. Because R is Boolean ring. Plus A plus 0 plus B, the same step was forward to the next step also on the RHS side. If we observe that, what is the left hand side part is there in the LHS? What is the left part? A. What is the right one? Right ending B. Here is also left is A and right is ending with B. Left in the LHS part, left is ending with A, starting with A, and right is ending with B. Here in the RHS part also, left is starting with A and ending with right side with B. By left cancellation law, we can easily cancel A on left side. Is it right? By right cancellation law on right side, B will be cancelled. We know that in rings cancellation laws works. That means we can use both left and cancellation laws at a time. By left cancellation law, A will be cancelled. By right cancellation law, B will be cancelled. Then what remains? A cancelled. AB is as it is. And plus BA was cancelled. BA is as it is. Plus B was cancelled. A cancelled, B cancelled. So the remaining part is A dot B plus B dot A is equal to, here also A cancelled, B cancelled. The remaining part is 0. Is brought forward. AB plus BA is equal to 0. What is the first bit? A plus B equal to 0. If we take A plus B equal to 0, then A is equal to B. Is it right? Similarly, if we apply the same condition for this also, this total is A, this total is B. A plus B equal to 0 means A is equal to B. That means AB plus BA equal to 0 implies AB is equal to BA. This is from 2, second bit. AB is equal to BA, A comma B from R. A dot B is equal to B dot A. That means R is abelian. That means we have taken in the first R is Boolean ring. R is Boolean ring. Now we prove that R is abelian ring. That means every Boolean ring is abelian. The theorem was over. Next, students, we learn the definitions. 0 divisors of ring. A ring R is said to have 0 divisors. We can say that a ring R has 0 divisors if A is not equal to 0, B is not equal to 0, then the product of AB must be 0. What is that? Two non-zero elements, A non-zero, B non-zero, but the product of AB must be 0. If this condition satisfies, then only we say that R has 0 divisors. R has 0 divisors. If what is the next definition is, the next definition, this is very important definition which will be used for the next definitions, that is no 0 divisors of a ring. That means a ring is said to have no 0 divisors. When, if it satisfies this condition, if you observe that here is there, you can follow the cursor. Friends, kindly follow the cursor. If A not equal to 0, B not equal to 0, then AB not equal to 0. In the 0 divisors, we observe that A not equal to 0, B not equal to 0, AB equal to 0. Here, no 0 divisors means A not equal to 0, B not equal to 0, AB not equal to 0, which is the opposite meaning. Here, 0 divisors, no zero divisors. Opposite na, the same one. A not equal to 0, B not equal to 0, product is 0. Here A not equal to 0, B not equal to 0, product is not equal to 0. The opposite is there na, the same one. If this condition satisfies, then the set R is said to have no zero divisors. There is another condition. You can use, instead of this condition, there is another condition can be used for to say that R has no zero divisors. What is that condition is, if the product is 0, if we are taking that A dot B equal to 0, then one of these two elements, either A